remember what we were saying about linear independent sets. So we said that if you have a linearly independent set, then everybody in the span can be expressed as a unique combination, right? Everybody in the span can be expressed in a unique way as a linear combination of those guys. So if you have a set of vectors that that is both linearly independent. So suppose you have a vector space, okay? You have an abstract vector space, and in that vector space you have a set that's a linearly independent set, and suppose it also spans the whole set, whole vector space. Okay? What that would mean is that everybody in the vector space can be expressed as in a unique way as a linear combination of the guys in the set. Okay, so that that motivates the definition of this thing called a basis. So you have V, a vector space, and if you have some set of vectors, so you have some set V1 through Vn that lies inside of V. Okay. If V1 through Vn spans V, and 2, V1 through Vn is linearly independent, then we say these guys are a basis of V. Okay, so any set that is both linearly independent and spanning is called a basis, Mia.
Sorry, what's spanning again?
Means that that the span of these guys is V. Do you remember what the span is?
No.
The span. Remember this. The span of these guys is the collection of all linear combinations.
Okay, yeah.
Okay. So if that collection of all linear combinations is the whole space, we say that this thing spans V.
Okay, yeah.
Right. So this translation is that the span of V1 through Vn actually equals V. Okay. So equivalently. Okay. Okay. So here's an example. You have you're given some matrix, right? You reduce it down to reduced row echelon form, and you're trying to find the null space of some matrix. Okay. So the null space of some matrix. So typically what happens is somebody gives you a matrix, and then you do the row reduction on it, and you reduce it down to something. Okay. And then you say, okay, you'd say, well, x1 plus 5x3 minus 3x4 is equal to 0. x2 plus 2x3 minus x4 is equal to 0. Right? And we've done this thing many times. Solutions look like something like this, right? Negative 5x3 plus 3x4, negative 2x3 plus x4, x3, x4. Right? In other words, they look like some number times negative 5, negative 2, 1, 0, plus some other independent number times 3, 1, 0, 1. Okay, we've done this thing before, right? The null space turns out to be the span of these two vectors, right? Negative 5, negative 2, 1, 0, and 3, 1, 0, 1. Now, these vectors are linearly independent, right? These vectors are linearly independent. So, in fact, are they are a basis for the null space of A. Right? We can't throw any one of these guys out. So this is an example of a basis, right? You have some matrix. You're finding the null space, and we find a basis for that subspace, for that null space. Okay. Everyone all right? Straightforward, I hope. Any questions? No? Okay. Okay. So that is the notion of basis. Next, the notion of dimension. So V a vector space, and you have some basis. Okay. We define the dimension of the vector space. It's usually written dim V as the number of vectors in the basis. Okay, so this thing means number of elements in. Okay. When you see this number sign, it generally means number of elements. So it means the number, right? So the dimension is defined to be the number of elements in any basis. Yeah, this number sign is usually read cardinality. It just means the number of elements, the cardinality of that set, the number of elements in that set. Okay. So if you want to find the dimension of a space, you just find a basis of it and count the number of elements in it. Right. So this thing is this thing has dimension 2. Because it's 2 elements in its basis. Okay. Now there's something a little bit unsatisfying about this definition. There's something that needs to be resolved about this definition, which is that you actually don't know, there's no guarantee at this point that all bases have the same number, right? You should say, well, you pick any basis. Well, how do you know that you're not going to pick 2 bases and end up with different numbers, right? Could it be that you have one basis that has 2 elements and another basis that has 3 elements for the same space? Okay, that won't happen, but we need to talk about it. So the question is, the problem is, do all bases? How do we know? This is well defined, right? That the number cardinality is the same, no matter what basis is chosen. Okay. So what will allow us to resolve that is the following theorem, where the result is kind of cool, but the proof is not at all interesting, or at least not particularly inspiring. But here, let me say it. If you have a set that spans a vector space, so again, B a vector space. Suppose you have a set that spans the space, and suppose that you have some number that's bigger than n. Okay. Then any set of vectors u1 through um must be linearly dependent. Okay, must be linearly dependent. So any set that is bigger than the spanning set must be linearly dependent. Okay. If we rephrase this from the point of view of the contrapositive, you say, well, if the set is linearly independent, then that tells you that that m must be less than or equal to n. Right. Is that clear? Right. Right. If m is bigger than n, then these guys are linearly dependent. If they're linearly independent, then it must be that m is less than or equal to n. Right? Okay. So in other words, what this theorem tells you is that the size of a linearly independent set is smaller than the size of a spanning set. Right? So cardinality of a linearly independent set, if you're in some vector space, the cardinality of a linearly independent set is going to be smaller than or equal to the size of the spanning set.
Sorry, what do you mean by cardinality?
The number of elements. Okay. So like if you have a linearly independent, somebody has a linearly independent set of vectors, and somebody has a spanning set of vectors that span the space. Well, this theorem tells you that the first set has fewer elements. Right? The number of elements in the linearly independent set is going to be smaller than the number of elements in the spanning set. Okay, Mia, yeah.
Is that because the linearly independent set is like a minimum kind of number?
Intuitively, yes.
Okay.
Yeah. So, and we'll see why it happens once we work out the proof here.
Okay.
Yeah. But yeah, so that's the intuition, right? The linearly independent set has some sort of minimality in it, and the spanning set may not. Okay. But before we do the proof of that, you can see immediately that the corollary is that, right, if V is again a vector space, and you have one basis V1, say U1 to UM, and you have another basis V2, which is V1 through Vn bases, then M has to be equal to N. Right. So the dimension actually is well defined. Dimension is well defined. Right. If you have two bases for the same vector space, then they're going to have the same number of elements. So you don't have to worry that somebody could end up with another basis that has a different number of elements. Henry.
What's the basis again?
The basis is so if you have the set which spans V and is linearly independent, then it's a basis. It's called a basis.
Okay. So if they're both bases, then they're equal?
Then they have the same number of elements.
Same number of elements.
Okay, so just to keep this concrete, to make it concrete, if you, in R3, this is a basis. These three vectors form a basis, right? Because they are linearly independent, and their span is the whole space. Okay, so this is what's called the standard basis. 1, 0, 0, 0, 1, 0, 0, 0, 1. The standard basis. Yeah, Mia.
Is there some sort of minimality in bases?
Yeah, because they have to.
Because of the-
They're linearly independent.
Okay.
Is that what you're referring to, or?
Yeah.
Okay, yeah. Yeah, so we want to set that spans the space and doesn't have any redundancy in it. Okay, that's what a basis is. And what we're seeing now, so we define the dimension as the number of elements in the basis, and what we're seeing now is that whenever you have two bases, then they have the same number of elements. Okay. Right. You couldn't, if you find another basis of R3, it's not going to have two elements. It's not going to have three elements. It's not going to have four elements, not three. Okay. Okay. But so does anyone see how you get from here to there? Why does it follow that if you know that the size of linearly independent sets are always smaller than or equal to the sizes of spanning sets, the number of elements in spanning sets, how does that, does anyone see how that immediately tells you that two bases have to have the same cardinality? So remember, a basis means you're linearly independent and you're also spanning. Yeah, Zane, go ahead.
That's what I was going to say.
Okay, good. So what?
So, therefore, they have, if the spanning set, or if a linearly independent set either has to be less than or equal to, and it's both spanning and linearly independent, they have to be equal.
Right. Can you make it a little bit more clear?
No, probably.
Okay, that's all right.
Okay.
Okay. So right, so I mean
That's
that's
the best I got.
okay. That's I mean that, so right. So each of these guys is both linearly independent and spanning, right? So Elena. Yeah.
So they both have to be greater than or equal to the other ones.
Right, exactly.
They have to be equal.
Yeah, exactly. Right. So because this is, so you think, okay, this guy is linearly independent and this guy is spanning. So the number of elements in this one must be, so m must be less than or equal to n. And conversely, this one is linearly independent and this one is spanning. So n must be greater than or equal to, less than or equal to m, right? Which gives you that m equals n. Okay. So it's an immediate corollary of the previous fact. Yeah, Ellen.
Are we going to show why
Yes,
that's-
right now,
okay.
right now. Yeah, I just jumped to the corollary to give you the punchline, and now we'll get our hands dirty. Okay. Any questions? Everyone with us? Okay. Okay. So let's do the proof. Like I said, the proof is not particularly exciting, but we'll do it. Okay, so let's see what we're trying to do. We're going to prove not the contrapositive, but the original statement. So you have more elements than a spanning set. Okay, so proof. Right. So we have we're given V1 through Vn, a spanning set, set of V, and we're given U1 through Um, where M is bigger than N, and we want to show that the UI are dependent. Okay. We want to show these guys to be linearly dependent. Okay. So in other words, we want to show that there exist coefficients C1 through Cm, not all 0, such that summation Ci Ui is 0. Right. all I've done is just write down translation. Okay.
What does the backwards E mean?
There exist. There exist. We want to show that there are coefficients. There are non-trivial coefficients, so that we get the zero vector. So we can get the zero vector out of this thing. Yeah, Mia.
What do the hats mean?
I just put hats on them.
Okay.
Yeah, why not? Hats.
Okay.
If you want, you can leave the hats off.
Okay.
But they don't mean anything. Okay, it's just their hats on them. Okay. Okay. So we have basically only one fact, right? That the V's span V. The V's span the vector space. So let's use that. We say, okay, well, like each, right, the VI's span V. So each UI can be realized as some combination of the VI's. So this Aij, Vj. So I've been kind of sloppy. I'm going to put vector signs on the U's and V's. J from 1 to n. Okay. Notice that that's an n. There are n guys in the VI set. Okay. So let's consider then summation Ci Ui, no hat this time.
Are they different than the other hat ones?
Well, so okay, so let me explain the hats then. Okay, so I'm going to use the hats as a specific instance of the guys without the hats. So the CIs are like,
Okay.
these guys are going to be variable, and then we're going to find specific guys of the specific instances of those, and those will be the guys with hats.
Okay.
Okay. So let's consider, just combinations. Right? Consider linear combinations. They look like this. We can replace the UIs with their expression in terms of the V's. Right? So this is going to be Ci summation Aij Vj, I from 1 to m, and j from 1 to n. And we just keep on going, right? We say, well, let's write this as summation j from 1 to n, summation I from 1 to m, Ci Aij Ci Vj. So I just reversed the order of summation. Instead of summing from over the i's first, I'm going to sum over the j's first. I'm seeing basically what the coefficients of the j's are, of the vj's. Okay. Okay. And at this point, we make a simple observation. We say, well, look, the system summation Aij Ci I equals 1 to m, right, equals 0 is a homogeneous system with m unknowns and as j goes from 1 to n, and n equations. Right, with m greater than n. And so we have a homogeneous system with the number of unknowns exceeding the number of equations, right? And so you know that such systems have infinitely many solutions, right? So it has non-trivial solutions. So take one non-trivial solution and call that C1 hat through Cm hat, and that will make all these things zero. So you find a non-trivial solution that gives you the zero vector. Right? Call one solution. Call one such solution C1 hat through Cm hat. And then use that guy. Okay. So this theorem is more like an observation than anything. Right? You just say, are these guys linearly dependent? Right? If you have a spanning set and you have more elements than the spanning set, can you combine them to get the zero vectors? Yeah, that boils down to solving a particular system, right? And that system has infinitely many solutions, infinitely many solutions. So that's it. Okay. Any questions? It's more like I said, a calculational observation than a real insight. Teresa.
How can you just describe the step again from like the system Aij
Yeah.
Ci
Yeah.
0?
Yeah. So we are looking for CIs to make this thing equal to the zero vector. Right? Right? We want to make this thing equal to the zero vector. We want non-trivial CIs. So that makes to make this thing equal to the zero vector. So let's look at it. What is this? We can rewrite this, rewrite this, rewrite this. Okay? And then from here we're saying, okay, well, let's make each of these guys 0. Right? If we can make each of these guys 0 in a non-trivial way, then we get the zero vector. Okay? So you say, okay, let's make a system. Let's make this into a problem. Here's the problem. We need to make each of the coefficients here 0. Okay. Right. And so we end up with a system of n equations. Right. There are n of these vectors. Right. We end up with a system of n equations and m unknowns. Right. The CIs are our unknowns. Okay. You say, okay, well, how many CIs are there? There are m of them, and there are n equations, and m exceeds n.
How do you know that m exceeds n?
Because that was our assumption.
Okay, that was
We're starting off with a set of U's that has more elements than the spanning set. Okay. And that's the key, right? Right. So this is exactly how it works, right? As long as you've got more elements than the spanning set, then you end up with a homogeneous system with more equations and unknowns, right? So it's like a translation. This question boils down to a homogeneous system with more equations, more unknowns and equations, and so you end up with non-trivial solutions. I wish I could say something better is coming. Yeah, look at the clock. Keep on looking at that clock. Tell me if it gets faster.
That's a call out right there.
When?
That was a call out right there.
What's a call out? I don't recognize.
It's like you like called me out on doing something.
Oh, I see. I see.
Yeah. The moment you said it's not gonna get better there, I was just like, oh gosh.
Yes, yes, yes. Yeah. And you should be. And you should be.
I should be afraid.
No, you should be like, oh my God, why? Okay. Okay. Yeah. Okay. So. Yeah, so there are a couple of theorems and corollaries. There, maybe like two more. There's a theorem and there's a corollary in this section. And like I'm sort of hinting, each of them is not particularly exciting. But let me just at least I'm going to state them. Okay. So let V be a vector space with dimension n. And let V1 through Vn be a set of vectors. Vectors in V. Okay. So you know the dimension already. Okay. You know the dimension already, and you have a set that's the right size. Okay. You have a set that's the right size. Then V1 through Vn is linearly independent if and only if V1 through Vn is spanning. Okay. So that is, if it's the right size already, then being a basis, you just have to know one of these facts, right? Because one will imply the other, right? You know, normally to show that something is a basis, you need to show that it's both linearly independent and spanning. But if it's the right size already, then being linearly independent is equivalent to being spanning. Okay. So maybe just for practice, see if you can write down a proof of this. Take 2 or 3 minutes and see if you can write down why one, you don't have to do both directions, do one of them. So show that one side implies the other side. Or you can do both ways if you like. Okay, would anybody like to give it a shot? Or maybe turn to somebody next to you and say what you're thinking about how you would phrase the argument? Talk.
What I did was, so the dimension is n, which means that the number of elements in the basis, and the dimension is linear independent, spans V. The number of elements in this thing that is linearly independent and spans V equals n. And so then if this is linearly independent, which means it's all unique combinations, then it has to be all of them.
I don't know,
You probably.
yeah, that's what I was like, if you know, the dimensions.
But I was thinking that if it was linearly independent, because there would be something inside the set that would be also right to linear dimension.
Yeah.
Okay. Who would like to say something and see how you can see how your expression is? Who would like to give it a shot? One way or the other. Haley, you're looking at me. You want to say? Which way? This linearly independent implies that it must span, or span implies that it must be linearly independent?
Well, either. Linear independent implies that it must span.
Okay, so suppose, let's say that these guys are linearly independent. So why must they then span?
Because the dimension of V is n, which means that its cardinality is n, and then V1 through Vn, its cardinality is also n.
Okay, so the dimension of V being n means that the cardinality of any basis would be n. Not that the cardinality of V is n, right? But that if you have a basis, it'll have n elements in it. V itself will have infinitely many elements.
So are we proving that it's a basis?
Yeah, so that's what we're showing. Yeah, we're going to show that this thing is linearly independent. In fact, it's going to be a basis, right? So we're trying to show that it spans V.
So we're trying to prove that it's linear independent to say that it's a basis?
No, we know it's linearly independent already, and we're going to show that it also spans, and is thus a basis. So one way you could do it is, for example, like saying, suppose it doesn't span. Okay. Suppose it doesn't span V. Right? And then you could go from there if you wanted. But
Well, if it doesn't span V, then it would have to have less, it would have to have more values than n, right?
Well, let's see. So if the span of this is not all of V, right? Suppose the span doesn't cover all of V, right? We know the span sits inside of V, but suppose it doesn't cover everything. Okay. Well, in that case, there'd be some guy in V that's not a linear combination of these guys, right? Right. In that case, then there exists some vector V n plus 1, say. Let's call it V hat, say. There exists some vector V hat in V such that V hat is not a linear combination of the VI's. Right? It's not a linear combination of the VI's. Right? Does that give us a contradiction? Yeah, sure. Well, we're trying to show that it's spans V, right? So how do we get a contradiction? So we have that these guys are linearly independent. We're trying to show that their span actually is V. Suppose it's not V, right? So by contradiction, right? Suppose the span is not all of V. Well, then there's going to be somebody in V that's not a linear combination of these guys. Okay. Does that give us a linear? Does that give us a contradiction somehow?
It's still not redundant, because if it's not a linear combination, then it's something different, and that's not redundancy.
Okay. Okay.
But-
So that means that if we throw this guy in here, we still have a linearly independent set, right? So then v1, vn, and if I throw in this v hat guy, is still linearly independent. Does that give me a contradiction? Is there anything wrong with that? I've got n plus 1 guys in the space, and they're linearly independent.
Then the dimension can't be.
Then the dimension wouldn't be n, right? Right? There's a contradiction because the spanning sets should be size n, but we've got sets that are linearly independent that are bigger than spanning sets. Right? So contradiction. Right? We end up with a linearly independent set of size bigger than spanning sets in the space. Right? Knowing that the space is dimension n means that we can find bases which are spanning sets which have n elements. But we've just created something that has n plus 1 elements and is still linearly independent. And that contradicts the previous theorem, which said that linearly independent sets should be less cardinality less than or equal to that of spanning sets. Right. So you say, but there are n plus 1 elements here, right? And so that leads to a contradiction, because you end up with a linearly independent set with more elements than spanning sets. Okay. Did anyone try the opposite direction? Suppose that the thing spans V, show that it is linearly independent. Yeah? Did you try? No? Let me sort of sketch it out for you. You say, well, look, suppose they span V and are not linearly independent, right? Suppose they span V and are not independent. Go backwards. Say that Vi span V, but are not linearly independent. Okay. In that case, one guy is expressible as a combination of the other guys. Then, without loss of generality, say the last guy is in the span of the previous guys. Right? So that means that the span of the previous guys span V. Right? That last guy was redundant. Even if we throw it out, the span doesn't change. Okay? What's the contradiction? Mia?
The dimension is n-1.
Right, the dimension is n-1, so we know that there are linearly independent sets of size n in the space, right? Now, dimension of V is n, so there are linearly independent sets in V, cardinality n. But that means we'd have a spanning set that's smaller than a linearly independent set, and that's a contradiction. Again, we contradict the previous theorem. Okay. An immediate corollary of the above theorem is the following: that any linearly independent set can be extended to a basis, and 2, any spanning set can be reduced to a basis. If you start off with a linearly independent set, well, you just keep on throwing in more vectors until you have a basis. If a spanning set, just keep on throwing out until throwing out the redundant ones until you have linear independence. Right? And either way, you're going to end up with a basis. Okay. So maybe that was not as boring as I thought.